What specific problem does your research aim to solve regarding the transferability of reasoning capabilities from mathematical to non-mathematical domains?
My research aims to address the problem of whether enhanced mathematical reasoning abilities in large language models, LLMs, can effectively transfer to non-mathematical reasoning and general tasks. We investigate this by evaluating over 20 reasoning models to determine if improvements in math problem solving translate to other reasoning domains, such as scientific question answering and instruction following. Our findings reveal a significant divergence in transferability, primarily influenced by the fine-tuning paradigm used. Specifically, models fine-tuned with reinforcement learning, RL, demonstrate superior generalization to non-math tasks compared to those trained with supervised fine-tuning, SFT, which often suffer from catastrophic forgetting. We quantify this transferability using a proposed metric, the Transferability Index, and conduct controlled studies to validate our observations, ultimately showing that RL-tuned models maintain better internal representation stability, allowing for effective knowledge transfer across diverse tasks.
How does the proposed method of transferability index work? Please illustrate it step by step, including its definition and how it is calculated based on benchmark results.
The Transferability Index, TI, is a metric designed to measure how well reasoning models can transfer their capabilities from one domain to another. It is defined by evaluating the performance of models across three categories of benchmarks: math reasoning tasks, other reasoning tasks, and non-reasoning tasks. To calculate the TI, the average of per benchmark gains is computed for each task group, which involves comparing the performance scores of models on these benchmarks. Specifically, the TI value is derived from the relative gains observed in the model's performance across these groups, with any TI above 0 indicating positive transfer. This systematic approach allows researchers to quantitatively assess the extent to which improvements in mathematical reasoning translate to other reasoning and non-reasoning tasks, thereby providing insights into the effectiveness of different fine-tuning methods.
Can you provide a simple yet illustrative example of how your proposed algorithm, specifically the RL fine-tuning process, operates within a typical reasoning task?
In our study, we illustrate the RL fine-tuning process using the uni-reason model, which is fine-tuned on a high-quality math dataset. For instance, during the RL fine-tuning, the model receives rewards based on the correctness of its answers to math queries, allowing it to optimize its reasoning pathways without explicit step-by-step supervision. This contrasts with supervised fine-tuning, SFT, where the model learns from teacher-generated reasoning traces. The RL approach enables the model to maintain a stable internal representation, as evidenced by lower PCA shifts and KL divergences compared to SFT models. Consequently, the RL-tuned uni-reason model not only excels in math reasoning tasks, but also demonstrates improved performance in non-reasoning tasks, showcasing its ability to generalize across different domains effectively.
What are the practical benefits of employing reinforcement learning over supervised fine-tuning in enhancing the transferability of reasoning models?
The practical benefits of employing reinforcement learning, RL, over supervised fine-tuning, SFT, in enhancing the transferability of reasoning models are significant. Firstly, RL-tuned models consistently demonstrate higher transferability indices across both reasoning and non-reasoning tasks, indicating that they generalize better to diverse applications beyond math. This is attributed to RL's ability to reinforce reasoning skills without severely perturbing the model's general domain representations, while SFT often leads to catastrophic forgetting and over-specialization. Additionally, PCA shift analyses reveal that RL models maintain a more stable latent space, resulting in minimal shifts in internal feature geometry, which is crucial for knowledge transfer. Furthermore, token distribution analyses show that RL models exhibit lower KL divergence and token rank shifts compared to SFT models, suggesting that RL fine-tuning preserves relevant task-related tokens while minimizing irrelevant shifts, thereby enhancing overall performance across various tasks.
How did you validate the effectiveness of your approach, particularly in measuring transferability across different reasoning and non-reasoning tasks? What metrics and experimental setups did you use?
To validate the effectiveness of our approach in measuring transferability across different reasoning and non-reasoning tasks, we introduced the Transferability Index, TI, as a quantitative metric. We evaluated over 20 reasoning models across 3 benchmark categories: math reasoning tasks, other reasoning tasks, and non-reasoning tasks, using accuracy as the primary evaluation metric. Our experimental setup involved fine-tuning the Quen 3-14B model using both supervised fine-tuning, SFT, and reinforcement learning, RL, on a high-quality math dataset, allowing us to directly compare the performance of these two paradigms. We conducted a controlled study where both models were trained on the same data samples, ensuring a fair comparison. Additionally, we employed latent space principal component analysis, PCA, and KL divergence to analyze shifts in internal representations and token distributions, further supporting our findings that RL-tuned models exhibited superior transferability compared to SFT-tuned models.
What limitations did you encounter with your method, especially regarding RL fine-tuning? And how do these limitations affect the generalizability of your findings?
In our study, we encountered limitations with the RL fine-tuning method, particularly concerning its reliance on the quality of the reward signals derived from the ground truth. While RL models demonstrated strong generalization to non-math tasks, the effectiveness of this approach can be compromised if the reward signals are not sufficiently informative or if the training data lacks diversity. This could potentially lead to overfitting on specific reasoning tasks, limiting the model's adaptability to broader contexts. Additionally, the controlled study's design, while effective in isolating the effects of fine-tuning methods, may not fully capture the complexities of real-world applications where diverse reasoning and linguistic capabilities are required. Consequently, while our findings suggest that RL-tuned models outperform SFT models in transferability, the generalizability of these results may be constrained by the specific training conditions and dataset characteristics employed in our experiments.